To talk about a balanced equation and its relationship to rates, the coefficients are proportionality of how the speed is changing. So N2O5, in this case reactant, is 2 to 4 for one of the products, NO2, and then it's also to 1 times of oxygen being produced. N2O5 is going to be consumed, so it's at beginning is fast, and then gradually it's going to slow down. So if we ask you to write rate in this case is change in concentration of N2O5 over unit time, delta T, but the 2 goes in the denominator, and we put a minus because you are being consumed. Then if we look at one of the reactants, NO2, this is also equal to positive because you are being produced. Concentration of NO2 changing over unit time delta T, but the 4 comes in denominator, meaning NO2 is twice as fast as N2O5. And if I want to draw that, we start from 0. At beginning you have nothing. It's extremely fast, so it's a steep slope, and then gradually it's going to die off because you don't have much particles left to collide. Now if you look at oxygen, the other reactant, the rate is also equal to change in concentration of oxygen per unit time delta T, and coefficient is 1, so in denominator we have 1. So oxygen is going to be produced at a rate which is 1/4 of NO2 because of the coefficient. And then again, compared to itself, it's fast at beginning, but then it's going to slow down. So this is concentration or change in concentration of oxygen versus the change in concentration of NO2 compared to concentration of N2O5. So if you know one rate, let's say per unit time, if I go after this segment, and let's say we are going to calculate for oxygen between 4 and 5 seconds the rate. So we make a slope, a gradient, and we calculate the slope, which is the change in concentration, your y-axis, over delta T. Delta T in this case is 1 second. The change in concentration, let it be 2 take away 1.8, so I'm going to say 0.2. So 0.2 mole per decimeter cube. So if I put this quantity up here, 0.2 mole per decimeter cube per second, we should be able to calculate the rates of NO2, which is 4 times as fast as this, which is positive 0.8 mole per decimeter cube per second. And we should also calculate the rate of N2O5, which is twice as much as oxygen, and it's negative 0.4 mole per decimeter cube per second. So a few things to remember. The steeper your slope, the faster you are. At beginning you are extremely fast, and this is usually referred to as initial rate. It's measured when time is approximately equal to 0, when you have lots of reactants, and that's what we usually want. As you are being used up, you will have a slower slope because you don't have much collisions. So those are a few things to remember, and that's basically it. So you have to be able to look at a balanced equation, and if one rate is given, be able to say what is the rate of the other reactants or products.